Okay, so fingers crossed. Hopefully this is going to do the trick. So back to graphing. So we looked at a graph of sine, a really rough graph of sine, particularly because my pen wasn't working very well. I'm going to regraph sine here right now, and we're going to see, some techniques that we can use to do a little bit more substantially good graphs of sine. So when I'm going to graph sine, or any trig function, frankly, you're going to find that often what I'll do is I will kind of put in some framing windows. And what I mean by that is as follows. So I know for this particular function, so if we think about this is going to be y equals the sine of x. Okay, and so I'm going to be graphing this. I'm going to add in some framing windows. So I know the highest that sine of x can get for the basic sine x, which is what we have here. I'd like some color, come back here. For the basic sine of x, the amplitude is 1. So the amplitude tells me how far from the center line I can get. So here we go, and here we go. So there's my amplitude lines, and then I'm going to add also a period length line. So period length tells me how far or how long it goes before it repeats. So I know for sine of x that the maximum value it can reach up to is 1, and then the minimum value is obviously going to be -1, and then this is going to be 0. Now, the period length of this function is 360 degrees. So I'm going to write in that this is 360 degrees. Now, sine, so what's unique about sine is it starts from the center line and it goes up and it finishes one full cycle in this 360 degrees. So by putting these framing lines in, it lets me kind of see an easy way of what the shape of this thing has to be. I know it crosses back through the x-axis, the halfway point, so I'm going to put like a little halfway marker in there. And so then I know it's going to go upwards to begin with. It's going to come across. It's going to come down, go through that as best we can. And then it's going to go cycle back up. And there it is right there. So that's one period length. Now, I don't want you to think that that's the entire graph. It does that over and over again, right? Like it just keeps on trucking up and down, up and down, up and down, and it keeps on going. And each one of those period lengths, even though I didn't do a great job here, that'd be another 360 degrees, so take me to 720. And another 360 degrees out to this one, so that'd be out to 1080. Okay, and then another 360 degrees out here, and that would take me to 1440 degrees, and it would just keep going. And similarly, it would go off in the negative side. But I'm going to always keep track of a bunch of things. So I know I'm going to keep track of what is the center line. So I'm just going to short form that as a center line. The center line for this one is at 0, as can be seen right here. That's the center line. It's got an amplitude. Okay, the amplitude is how far away it can get. And I know, because I've done this a bunch of times, that the amplitude for this function is 1. The period length, okay? The period length that I'm keeping track of here is how far it goes to repeat, and it is 360 degrees, okay? And then the final one is the phase shift. And the phase shift tells me how far left and right our function has been moved. So the phase shift for this one is going to be 0. Now, if we think about some functions there's going to be transformations that happen to functions. So if we think about quadratics, we thought about, like if we think about vertex form had y equals a bracket x minus h bracket squared plus k. Okay, so just off as an aside, right? If we think about an aside here, I'm going to make my brush a little bit bigger. If we think about an aside for that, when we had y equals a bracket x minus h bracket squared plus k, this told us how far left and right we went. All right, that was how much left and right we went. This is how much up and down we went. And this was the stretch factor. The stretch factor told us whether it was made really skinny or really wide by either stretching it up and down or by compressing it from up and down, okay? Well, sine x has a similar, so this is kind of the general form that we can use for transformations, right? That was transformations of quadratics, trans of quads, right? That's what we had for quadratics. Well, there is a similar thing that we're going to go through and we're going to learn about for sinusoidal functions. So I'm going to write the general form, and that is y equals a ber sine of bx plus c, and we're going to put those guys in brackets, plus d. Okay, so if I were doing this in class, we'd spend a lot of time exploring with Desmos or all of those things. It's going to be more of a challenge from a distance. And so what I'm going to do is, I guess the easiest thing for me to do is to talk about what each of these letters are without some experimentation. If you want to experiment at home, I would suggest it's a great idea. And so I'm going to write a few different functions. If you're at home, you can drop these into Desmos, and Desmos will show you some graphs, and you can make some conclusions on your own. So the first variable we're going to talk about, okay? So the first variable we're going to talk about here is the A variable. So I'm going to write out a series of these, and you're going to be able to, hopefully, if you take the time, you can go and play in Desmos, and you can probably get a pretty good idea of what exactly is going to go on. So if I would get you to do y equals 3 sine x, and then the sine x is going to be the same for each of these things. So 3, and then y equals 5 sine x, y equals 1/2 sine x, and how about y equals -4 sine x, okay? So sine x on each of those guys, give those a whirl, and come on back if you've got it. If not, I'm just going to talk about what that is. So the A it's the exact same A, as a matter of fact, as what it was back when we did quadratics. What the A tells me is it is actually the control of the vertical stretch or compression or reflection across the x-axis. So if we think about a negative A back in quadratic times, a positive A up here, positive A went like that, right? That was the positive A. If we had a negative A, it opened downwards. And so we talked about being happy versus sad. What was really happening is it was being reflected across the x-axis, and the same thing will happen here, okay? So the A is an indicator of, it is the amplitude, because if we think about amplitude as how far away from the x-axis we can get, A is the amplitude. It controls the vertical, so the up and down, stretch, and reflection. This is still not working as well as I would hope, but nevertheless, here we are. Okay, so it's the amplitude, it controls the vertical stretch and reflection. Okay, so some examples of that. So if we had to graph, okay, so let's look at some examples. We are going to graph, well, let's do these ones up here. So I'm going to graph y equals 3 sine x. So y equals 3 sine of x. Okay, so I'm going to grab me some axes here. So I'm going to draw on my axes. Okay, so oops, stop that. When I'm going to have you graph these things, I'm going to always ask you to graph 2 full cycles. So maybe I'll put that here. So I'm going to say graph 2 full cycles. Now, A is the amplitude. It actually is the number that tells us how far from the center line we can get. Well, if we think about this one, for the center line for this guy, it can get 3 away. So instead of being a max and a min value of 1, it's going to have a maximum value of 3 and a minimum value of -3. So I'm going to go ahead and I'm going to, you don't always, like, this is certainly optional, but I think it's a good idea. I'm going to draw in my framing window to help me sketch these things, okay? So there we go, there we go. And I'm going to draw 2 cycles. So there's going to be my first cycle, and I'm going to draw another one that's the same size, and there's going to be my second cycle. Now, The only thing that we're going to actually be changing about this particular function is the amplitude. The amplitude is now 3 instead of 1, because even though it didn't explicitly say it, when we graphed y equals sine x, it's understood that there's a 1 there. Okay, so everything else stays the same. Now it's going to look almost identical because I haven't drawn it on the same scale. But if we put in the original function, right, so I'm going to maybe grab a different color here, whatever color this is. If I put in the original only went up to 1 and down to -1. Okay, so this would be regular old y equals the sine of x. And so regular old y equals the sine of x. It's going to be halfway there, and it's going to be halfway here. And then it's going to say, well, regular old sine x is only going to get up to that 1. And then it's going to smoothly come back down underneath, get down to -1. And then it's going to go back up, and it's going to go over, and it's going to come down. And there's regular old sine x. It only has an amplitude of 1, right? So this distance in here is simply 1. But if we think about 3 sine x, let's see if I can get the same color back. I don't think that is, but nevertheless, 3 sine x is very, very similar. But instead of only being limited to being 1 away from the x-axis, it can get 3 away from the x-axis. Okay, so it can reach all the way up to 3, but it's got to follow the same period length, the same length to do the same thing. So it has to cross through the x-axis in the same places, right? So if we're tripling the distance from the x-axis, which is effectively what is happening here, then what we have is if the distance from the x-axis is 0, which it is when it crosses, tripling 0 is still 0. So there is 3 sine x. So the only thing that changed about this function was the amplitude. It has an amplitude of 3 instead of having the amplitude of 1 of the original function. And you can imagine that if we did it for 5, it would be, again, the exact same thing. So if I wanted to do it with 5, maybe 5 would be, I have no idea what color that is. It's greenish, I think. Maybe 5 is up here, and then -5 is down here. So y equals 5 sine of x. Well, it would look very similar, but it would be even taller. It would go all the way up to 5. We'd still have to cross down in the same position here, come down underneath. We get down to -5, and then it would have to rebound and go back up. Now, it's hard to do this like this, but it should be quite smooth. Those should be nice peaks that are smooth and curvy. I know it's not the greatest here. And so that is what y equals 5 sine x would look like. And then similarly, half sine x would be, well, it would kind of come in this spot here. It would only have a maximum of a half and negative a half. So it would be even smaller. So the A value, what it controls is the amplitude. It is how far it gets vertically stretched. And that's what it does. That's what the A value does. Now, in the event that we get an A value that is negative, so I'm going to do this as a separate graph here. So if we had an A value that's negative, so let's grab a different color, whatever color that is. So if we did y equals -4 sine of x, okay? So if we go ahead and we want to graph that fella, so what we're going to do is, I'm going to still put in the axes. There it is. And the magnitude just means how big the number is, doesn't matter whether it's negative or positive. So the amplitude for this one, I have no idea what color that was again, this one. So the amplitude here for this is, it is still equal to 4, because amplitude tells us how far away it gets. So even though this is -4, amplitude just tells us how far, how long something is. Like, if a board went downwards, we wouldn't say that the board's length is -4 feet. That doesn't make any sense. The amplitude is how far from the center line. So if you put a tape measure on it, it would be still 4, whether we measured upwards or downwards. So the amplitude is 4. So that means it can get 4 away from the center line. So this is going to be 4, and this is going to be -4. And I didn't really draw them in, but let's draw those window framers in. So there's a window framer. I'm still going to draw 2 cycles. Here's a window framer as well. got this guy, got this guy. Now, period length hasn't changed at all, right? So the period length still is 360 degrees and 720 degrees, right? That's my period length. And what we have now, if this was positive 4 sine x, it would be looking the same. It would go up to the 4, come back down, go underneath, and it would be the exact same. Because this is negative 4, what it has the implication of doing is that it reflects it across the x-axis. So positive 4 would go upwards to begin with and go like this. Negative 4 says, no, you don't go upwards to begin with, you go downwards to begin with. So it still has to come through at the halfway point, and it still has to come through at the halfway point here. But negative sine for sine x is going to look like this. Okay, so it really was meant to get all the way down there like that. Come up and go through. Go down through, and then we're going to repeat a second one, right? Get all the way down there, up, and then back, and there it is, okay? So the a value in y equals a sine x, what it does is it controls two things. It controls just how high or how far from the center line we can get. So we can get 4 away, right? We can get 4 above or 4 below, but the distance in each of these cases is 4, right? So it tells me how far from the center line we can get, but it also tells me whether it goes upwards to start or it goes downwards to start. And for sine, if it's positive, it goes upwards to start. And if it's negative, it goes downwards to start. So that is the a value with respect to sine. Okay. Now, next thing that we're going to jump to, I guess the next thing that we'll jump to is the d value because it is the next easiest thing to deal with. So if we think about y equals a sine of bx plus c plus d. What we're going to look at right now is we're going to look at the d value. Again, if you want, go off to Desmos and you can play with it. Certainly that's what we would be doing if we were in a live classroom. So we have y equals, let's just start with the basic one. So sine x, we know what it looks like. How about if we said the sine of x plus 3? How about if we said the sine of x plus 1? How about if we said y equals the sine of x minus 4? So go ahead, go off to Desmos and give those a whirl and see what they look like. And I bet you can make a direct conclusion of what it's going to be. For those of you who aren't willing to go and play on Desmos, here's what we're going to get. The d, okay, so the d value, it's as simple as it is the position of the center line. Okay, so that tells us exactly where the midpoint, okay, it's often called the axis about which this is fluctuating. It's, it is the center line of the function. Okay, so if we consider the graph of y equals sine x plus 3, so let's do that one first. So y equals the sine of x plus 3. So I'm always, when I'm doing graphs properly, I'm always going to identify first what the amplitude is. Now, the amplitude in this case, remember the amplitude comes from the a value. Well, there's no a value specified, so the amplitude for this one must actually be 1. Okay, so the amplitude is going to be 1. And then we're going to look and we're going to say, all right, this thing has a center line. The center line is actually going to be 3. Now, period length, we haven't changed anything about. It is still 360 degrees. Okay, that's the period length. And then the phase shift is how much gets moved left and right. We haven't really talked about that at all yet. Phase shift is going to be 0. So now I'm going to sketch this thing. So here we go. I'm going to draw on my axes. Now I'm going to make it axes look a little bit different this time for no good reason other than it's just going to work out nicely. Now, this is still 0, right? This is still the x-axis, and this is still 0 for the y-axis. However, what we've got now is I have a center line of 3. So I'm going to draw on my center line. And again, I'm going to do that whole framing exercise. So I'm going to put a line in for the, oops, stop that. I'm going to put a line in for the center line. Okay, so here's my center line. There it is there. Now, amplitude of 1. The amplitude tells me how far away from the center line I can get. Here's my center line. 1 up from that takes me to 4. 1 down from that takes me to 2. And I'm going to draw in my framing windows for those ones. Okay, so there it is there. And there it is there. Okay, now period length is still 360 degrees, and I still want to draw 2 of them. Okay, so I'm going to draw my framing window this direction, draw another fellow here like this. So this is going to be 360 degrees, and this is going to be 720 degrees. Okay. And what we're going to have next is we're going to say, all right, it's sine. The A value is positive because it's not showing that it's negative, so it has to be positive. It always starts from the center line and goes upwards, and it stays inside of our framing window. Now it has to, of course, go through the halfway point. There it is there. So that'd be 180 degrees. Go through the next halfway point. That'd be 540 degrees. And it's positive, so it goes upwards to start. Gets up to that. And then it starts coming back down. Goes through there. Bounces off the bottom. Keeps going. And then there's one full cycle. And I'm going to repeat it for the second because I always want to sketch 2 cycles at least. Okay, there it is there. Comes back down. Goes up. Okay, so the D value is the position of the center line. It's also known as being our vertical, so vertical translation. Okay, it is a vertical translation. It's how far up or down the function gets shifted. Okay, so in this case, it was shifted up 3. If we did it at +1, the center line would be at +1. It would reach up to 2 and down to 0. If we did it -4, the center line would be at -4. The maximum value it could reach would be -3. The minimum value it could reach would be -5. Okay, so I'm going to write down a few functions for you to try and practice. And then tomorrow, what we're going to do is we're going to look at what the B and the C values do in our sketches of y equals sine x. They're more complicated. And then on Wednesday, what we're going to do is we're going to look at all of those same transformations, but we're going to do them with cosine of x. Awesome.